Okay. Well, good afternoon and welcome to the Lifelong Learning Program for Fall 2020. And welcome to the Geology and Natural Disasters. And I've been informed that this is the first trial run of the new hybrid format. So we're all the guinea pig today. So hopefully everything works out. And if it doesn't, if we got some issues, just please bear with us. So my name is Heather Merchant, and I'll tell you a little bit about myself before we begin. I have a BS in Geology from Wichita State University and an MS in Earth Environment and Physical Science from WSU as well. And my master's research was in structural geology. So I studied faults and fractures in western Kansas, originating from the Laramide orogeny, or the building of the Rocky Mountains. And I'm still a student as well. I'm a couple classes away from having my MBA in marketing done, so I'll probably just always be a student. I am a huge fan of the lifelong learning program. I think it's fantastic to just always keep learning and new things and keeps you active. So I taught oceanography for the program last year, and I had a fantastic time. So this is the second time I'm teaching for the program. And I'm hoping, although I can't really tell with the masks on, but I'm hoping a lot of you are the same students that I had last year, because I had a ball with you guys. So let's get started. Okay, so this is week 1. We're going to cover the natural disasters of volcanoes. I thought we'd start out with something flashy and a lot of fun. So I think volcanoes are the most fun of all of these. So we're going to cover several topics. First, we're going to do a basic overview of plate tectonics. Now, most of you, especially if you've taken a geology or an earth science class before, you're probably familiar with the theory of plate tectonics in some way, but this will be a good way to brush up on that. And before we can really understand natural disasters, and especially volcanoes, we really have to understand how things are being driven, what's happening, what's causing the volcanoes. So not only is it going to help with volcanoes, but then later on in the other classes, we're going to need to know a little bit of that plate tectonics as well. So I thought we'd start with that. We're not going to get too in depth with it because that could be a whole class in itself. So we're just going to learn the basics of it. And then we all have an idea of what volcanoes are. We all think Hawaii usually, but we're going to find out exactly what are volcanoes, what defines them. And we'll move on to the different types of volcanoes and how to live with volcanoes. How do they affect our lives? Even when we're far away from a volcano like we are in Kansas, are volcanoes affecting us right now? And then the fun part, we're going to go over historic volcanic catastrophes. And then we'll move into eruption forecasting. So geology and physical science, earth science, you can learn about it, you can read about it, you can look at pictures of it, but it's best learned when you can experience it. So since we can't go out and actually go visit a volcano, of course, so I've put in a few little short, like 2 to 3 minute little videos throughout so we can actually see some of the stuff that's going on. Okay, so we're going to start with our overview of plate tectonics. So before plate tectonics was a theory, there was Alfred Wegener. He was a German scientist and explorer. And he started noticing that the continents looked like pieces of a puzzle that could be pushed together. He wasn't the first one to notice this. Going back about 400 years ago, scientists started thinking that they could have possibly fit together and maybe broken apart. But Alfred Wegener was the first one who started putting lines of evidence and created an actual theory out of this. So, in addition to looking like puzzle pieces that could be pushed together, he noticed that there were fossil lines that went across the continents. Not just animals, but plants as well. And if any of you are gardeners, I love to garden, but if any of you are gardeners, you know that we're in zone 6B. Now, if we take a plant from zone 10, like a tropical hibiscus, and we plant it in our zone, come wintertime, it's going to freeze and die. So plants have a very defined ecosystem or environment in which they can live and thrive. Well, as you can see from this image, there's a fossil plant, and he found it not only in Antarctica, there were fossils of it in Australia, India, Africa, and South America. And these were all found in the same aged rocks. So how could the same plant live in so many different climates? It just didn't make sense. So that was another line of evidence for the continents all being together in a similar climate at one point in time. Then he also found glacial sediments in the tropics. And the tropics are very warm. There shouldn't be glacial sediments. They would have melted. So these all led him to believe that definitely the continents were together at some point. The problem was he didn't know how. How did they get together? How did they break apart? So he lacked a driver for his theory. Now, European geologists at the time, they thought, well, this is good enough. His theory looks pretty sound. Maybe he doesn't know how they move together, but, it sounds pretty good. I think we can go forward with that as a theory. And they pretty much accepted it for a while. American geologists, they didn't agree with that. They just said, no, you have to have a way that it's moving. There's just no way that continental crust can move and plow through the heavy basaltic ocean crust. So you got to have a driver. So between the 1910s and the 1950s, science ultimately rejected his theory. And he was an explorer, and later in life, he was exploring, and sadly, he froze to death. And it's very sad because he froze to death before he ever saw his theory of continental drift be incorporated into the theory of plate tectonics and have it accepted by science. So fast forward to World War II, and we have a geologist named Harry Hess. He was also a captain in the Navy, and he was assigned to a ship that was using new technology for the time. It was sonar. And at that time in history, it was still believed pretty much that the ocean basin was truly what you would think of as a basin. Very smooth, very flat, not much going on, just maybe some sediments precipitating out of the water column and creating a very, very flat, uneventful ocean bottom. Well, with his sonar, he was noticing that the water was different depths. So the basin in some points was very deep, other points it was very shallow where it should have been deep. So he ultimately discovered a mountain range on the bottom of the ocean. And this was the Mid-Atlantic Ridge. Now, already being a geologist, he was thinking in scientific terms and earth science terms. So he thought, how can there be a mountain range on the bottom of the ocean? It had to come from somewhere. So he thought maybe lava is coming up and building these mountains. And as it comes up, it would push the rest of the basin outward. And it would just get bigger and bigger and bigger. So he also understood that if you're creating crust and you're getting bigger and bigger, that would mean that the Earth would be getting bigger and bigger. But it's not. So where is it going? So where you create something, you have to destroy it if you're going to stay the same size and stay in equilibrium. So he discovered these trenches where it was very, very deep. And he discovered subduction. And that is where the crust gets subducted under another plate. So it would go like that, down under. So you'd have creation at the continental ridge and then destruction at the trench. And this kept the Earth the same size. And it also was the driver for moving the continents around the globe. And so before we get any farther, I wanted to show the layers of the Earth and where this movement is taking place. So at the deepest points in the middle of the Earth, we have the inner core. The inner core, although it's at the hottest location, you'd think it would be melted, but due to the pressure above it, it's actually a solid. It's mostly iron and nickel. And then when you get to the outer core, the pressure is far less, so it's able to melt. So it's believed that that's molten. And then we move up to the mantle. It's still hot, but not hot enough to be completely liquid. So it's soft, it's pliable, it can move. And that's where the magma is coming from in the upper mantle, and it breaks through the crust. So now I'm going to show a little animated feature, and it'll show you seafloor spreading and how it moves out. It also is going to demonstrate the switch in polarity. And this is another fact that helped to prove plate tectonics. At different times in history, and it's not known why, it's a mystery, the polarity of the Earth switches. North will become south and south becomes north. This is recorded in the rock record, the polarity of north versus south. So at the spreading centers, it's like zebra stripes, but they're mirrored on both sides. So that demonstrates that something is coming up from the center and moving out, because you would have rocks that are facing north, coming out, moving out, and then south, and then north. So you get these striping effect on either side. And that's what this animation is going to demonstrate. The internet's just a little slow in here. They take just a few seconds to start. So you can see it's spreading and it's coming up, and the compass is showing you when it switches polarity, and it gives that striping effect. And so it's pushing the continents away, and it's building this ocean basin. Okay, and that leads us to the theory of plate tectonics. And by definition, it is the theory that Earth's outer shell is divided into several plates that glide over the mantle, driven by seafloor spreading. And since the time when Harry Hess discovered plate tectonics, all the advances in technology and science, they've helped to support this theory. So far, there's been nothing to contradict it. Satellite imagery has been a huge help. It actually demonstrates how fast and where the plates are moving. And this is coinciding with where we believe the subduction zones are. So far, everything has supported it. Here's a short little video that's going to sort of sum up plate tectonics, and you can get a visual of how things are actually moving and what's going on.
During World War II, scientists at sea were using sophisticated echo technology to track submarines when they turned up surprising information about the ocean floor. There they found a stretch of underwater ridges made of continually erupting volcanoes.
The mid-ocean ridges formed when molten rock rises from inside the Earth and then pushes the crust apart.
A vast spreading seafloor strong enough to move the continents. Not only is new crust formed at mid-ocean ridges, but it dips back down again into the interior of the Earth.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
When two plates collide, sometimes one is pushed downward and melts into magma. Eventually, this red-hot material rises to the surface and explodes, creating a volcano. So new crust is born at mid-ocean ridges and destroyed at deep ocean trenches, like a never-ending conveyor belt. And two plates simply nudging each other can cause catastrophic results, like when the San Andreas Fault slipped in 1906. How fast do the plates move? If you live in the US, you're probably standing on the North American plate. In the course of 1 year, the ground under your feet will move about 2 inches. And over long periods of time, that's enough to reshape the Earth, build mountains, trigger earthquakes, and create volcanoes.
Here we can see it's a map of the globe, and it shows where the plates are, the plate boundaries, and what type of boundaries they are. So there's different types of boundaries. And the interesting thing is, we tend to think, when we think of a plate in our mind, we think of the shape of a continent. But the plate encompasses the continent and ocean basin around it. Or a plate could simply be ocean basin. And the plates are not always static. They've changed throughout time. Some of them are very old indeed, and then others are fairly new. So it just depends how they're breaking apart, where new crust is being created. So they change over time. But we can see the North American plate, and there's a little tiny piece of California that's actually sitting on the Pacific plate. So all of our country is not on one plate. And this is why we have earthquakes in California. This is a transform fault. So we'll get into the different types of plate boundaries in a minute. But this particular one, basically, they're sliding past each other. Nothing's being created, nothing's being destroyed at this point. They're just sliding past each other. And the Pacific plate is moving up while the North American one is coming down. So what happens is continents are not smooth. So they'll get kind of stuck and they can't move. And then all of a sudden the pressure breaks loose. And then that's when we have an earthquake. And that can be a small one or it can be a gigantic one. It just depends how much pressure and how much rock is moving and being broken off. So a fun fact is, and none of us will ever see it, but at some point in time, Los Angeles and San Francisco will be side by side. So they'll basically be the same city, if they're still around. Let's see. And you can see, like on the African plate, it's Africa, but it also includes a lot of ocean around it. It's actually in a similar shape to the continent, but it includes a lot of that ocean basin. And on the South American plate, you can see on the western coast, it's showing that there's a subduction zone right there. So the plates are coming together, and the Nazca plate is going underneath the South American plate, and that's where we get the Andes Mountains. Sure. Okay, so there's 3 different types of plate boundaries. And the first kind is divergent. So things are diverging, they're separating, they're moving apart. This is what the Mid-Atlantic Ridge would be. This is the type of boundary it is. So we're creating new crust, we're moving apart. This usually occurs along spreading centers where magma is being pushed up from the mantle. It can create volcanoes, volcanic islands, and it can also create rift valleys. So usually it occurs where 2 ocean basins are coming together, but it can also occur on a continent in between two continental crusts. And one place where that's happening is in the East African Rift Valley. And it's in Ethiopia mostly. And a few years ago, that was on the news because they had a remarkable movement in just a few hours. It moved feet. So basically what's happening is the African continent is being torn apart in that location. And as it's moving outward, the ocean is rushing in. So at some point in history, in the future, it's actually going to become an ocean, a new ocean. So it's very exciting, and that's a plate tectonics that we can actually see and witness right now. Another location where that occurs is in Iceland. You can go diving in Iceland, and you can be right in between where the Eurasian plate is pulling away from the North American plate. So you can dive down and you can touch both plates at once. So you can be in North America and Eurasia at the same time. So it's a fun area. And that's also why Iceland is so warm. They have a lot of hot springs. It's warm. It's very green. It's from that volcanic activity in the area. And then we have convergent plate boundaries. And they're a little more complicated than divergent. There's actually 3 different types of them. So when things are coming together, you could have a continent coming together with an ocean. So you have continental crust hitting up against oceanic crust. Well, when 2 things hit up together, that's a lot of force, and it's going to have to go somewhere. So they're going to have to go up or go down. And continental crust is very lightweight. It's very buoyant. And that's because of the minerals in it. We call it felsic. So there's a lot of potassium feldspar. There's a lot of silica in it. It's a lot of granite mostly. So it's very light. It's very buoyant. Oceanic crust is very dark. It's mafic. So that's magnesium and iron. So it's very dense. It's very heavy. So when you have something that's light coming up against something that's heavy and one of them has to sink, the heavy one is going to sink. So it gets pushed underneath the continental crust. So as it's going down, as it slides, you can see from there, it's sliding down, and as it gets deeper and deeper, it starts to get hotter and hotter. As so the crust starts to melt. Eventually, it becomes magma, and it has to come up. So that's where we get volcanic arcs, so like a series of volcanoes on the continent. Then we can have a continent coming up against a continent. So they're both light, they're both granite. So just from pushing, mostly what you're going to have is mountain building. You're going to just crumple upward. Now, a little bit of it's going to get pulled down underneath the other one. Not a whole lot, but a little bit. And once in a while, you can get a little bit of volcanic activity, but that's pretty rare. Mostly, you're going to just get mountain building. And then you can also have ocean to ocean. And this is very rare. It doesn't happen that often, but it can happen. And the older basin, whichever plate is older, it's going to be colder. It's going to be cooler. And so when things are cold and cool, they're more dense, they're heavier. So the older plate is going to subduct under the younger plate. And this causes earthquakes. It can also cause volcanism. This is how the Aleutian Islands was created, an ocean coming up against an ocean. And there's a cycle to diverging and converging. We open up ocean basins and we can close ocean basins. So if you have an ocean coming up against an ocean and one side is getting subducted, you're going to subduct down until there's almost nothing left. And then they're going to continue to come together until the rest of that ocean is squeezed out. And pretty soon, you're going to have continent up against continent. And so the same goes for when you're opening up. If you open two continents up, you're eventually going to create an ocean basin. So this whole cycle of opening and closing ocean basins is called a Wilson cycle. And then the third kind is the transform plate boundary. And this is what we talked of before, like California with the earthquake. So the two plates are just sliding horizontally past each other. So this is what the San Andreas Fault is. And these do not cause any volcanism, but they do cause earthquakes. They can cause some metamorphism in rocks because the moving past each other, it does create heat. It doesn't create enough heat to completely melt something, but it can just warm up the rocks to change their shape and convert the minerals. So before we finish up with plate tectonics, here's just a few little fun facts. So in that video that we watched, they were showing that the plates move about 1 to 2 inches per year. Well, a more fun way of saying that we usually use is to remember it, is they move at the same rate as your fingernails grow. So you could watch your fingernails, and as they grow, that's about how far you've moved on the plate. The Eurasian plate is the slowest, and the Pacific plate is the fastest. So plates don't necessarily move at the same rates, but on average, it's about 1 to 2 inches a year. And so in an entire lifetime, you'll be approximately 6 to 13 feet in a different location if you're living in the same city. You'll be about 6 to 13 feet in a different direction than you were when you were born. Okay, so now we're going to move on to what are volcanoes. So a volcano can be any time the Earth's crust is ruptured or cracked and hot magma from below is coming up. The official definition is any hill or mountain constructed by the extrusion of lava or rock fragments from a vent. And here's a short little video so we can see some fun. It'll show a few volcanoes erupting and sort of give us a brief description.
planet has a violent soul. Majestic and often destructive, volcanic explosions rattle our collective imagination. Krakatoa, Mount St. Helens, Etna, Eyjafjallajökull, the images simultaneously strike fear and awe in our hearts. But how did these giant mountains form, and where does all that destructive force come from? At least 50 eruptions rock the Earth each year, meaning our planet is literally bursting apart at the seams. The Earth's crust is made up of about 17 slabs of land called tectonic plates that float on the superheated magma that makes up most of the planet's interior. Magma is the Earth's lifeblood, churning restlessly beneath the crust. And wherever it can, it's trying to burst through. It's at these spots that volcanoes form. Our planet is home to some 500 active volcanoes. While some volcanoes, like those in Hawaii, break through a thin point in the crust called a hotspot, the vast majority of volcanoes occur on active fault lines where tectonic plates meet. The most volatile region is the Ring of Fire, a geological fault belt that rims the Pacific Ocean and holds roughly 75% of all the Earth's volcanoes. Typically, volcanoes take one of two forms. Shield volcanoes, wide and broad with lava usually slowly oozing out of them, and composite or stratovolcanoes, steeper and more violent. When hot liquid magma reaches the surface, whether in a slithering flow or a booming eruption, we call it lava. Though molten lava may seem threatening, it's not known to move quickly. A volcano's pyroclastic flow is far more deadly. This poisonous ash cloud can race down the slope of a volcano like a bullet train, obliterating everything in its path at speeds topping 100 miles per hour. It's what stopped the residents of Pompeii dead in their tracks. But despite the volcano's brutal destruction, it is also a force of beauty and rebirth for the planet. Lava creates new lands where life can flourish. Like it or not, volcanoes are part of the planet's life cycle. As the Earth continues to explode, gurgle, and slither its molten heart out, we must learn to live side by side with its awesome power.
And before we go any further, she did mention that Hawaii was formed by a hot spot. What a hot spot is, it's a location where nobody knows why, but magma cracks through the crust. It's just a spot on the crust where it's a little thinner, and for some reason it's able to come through. And so what happens is the hot spot remains static. It stays in one place where the magma is coming up. And the continent, or the plate, oceanic plate as well, it'll move over it. And as it moves over it, it'll create one island after the other. So that's how Hawaii was formed. And if you look at the location and measure the location of like the first island and the last island, you can calculate how fast the plate was moving based on the ages, and also which directions the plate was moving. Okay, magma versus lava. You've probably heard both terms used in reference to volcanoes. And although some people think it's the same thing, it's actually not. The only difference between the terms is location. So they're referring to the location of where the melt is. Magma is below the surface. And since it's below the surface, it's generally hotter than lava because it's near the heat source. Lava is above the surface, so it's a little bit cooler. But the same melt, if it's an active volcano, it should have both magma and lava. And again, it's the same melt. It's just you use which term depending on where that melt is, whether it's below the surface or above the surface. If magma cools and becomes rock before it becomes lava, we refer to those rocks as intrusive rocks. They were formed inside. Intrusive rocks have much larger mineral crystals in them because they took so long to cool. So the crystals had a long time to grow. Rocks from lava are just the opposite. They're above the surface, they're away from their heat source, so they cool and lithify into rocks very quickly. So the crystals don't have much time to cool. So that's an interesting way that when we're examining rocks, we can tell if it crystallized out of a magma or a lava. So types of volcanoes. In that video we saw, she spoke of two kinds, the composite and the shield volcano. Generally, science considers there to be 3 volcanoes, but it depends who you're talking to. Some insist that there's 5 types of volcanoes, some will say 6, and some will say 7. And the others are not necessarily volcanoes in the sense of when we think of a volcano, when we're thinking Hawaii or Mount St. Helens. They're just different forms and different ways that magma is coming up to the Earth's surface. So I'm going to cover 5 of them, and these are the types that you generally think of when you think volcano. So the first is shield volcanoes. Probably one of the most common, and when we think of a volcano. I mean, we all think Hawaii, right? And these volcanoes, they're called shield volcanoes after Roman shields. So they're round, they don't have a lot of relief, they're not very tall, they have very gentle slopes between 2 and 10 feet. And in Hawaii, they only rise about 10 kilometers from the seafloor. So they're not very tall in terms of mountains or other volcanoes. They're very, very short. They have basaltic lava. So it's very similar to what you saw coming up at the spreading centers. So basalt, again, it's very heavy, it's very dark, a lot of magnesium and iron, and it has a pretty low viscosity. So it's fluid, but it's not like water. So water would be high viscosity, toothpaste would be low viscosity. And even though you might if you squirted toothpaste out here and you look at it, it wouldn't look like it's moving at all. It wouldn't look like it's flowing. But leave for a day and come back, and you'd find that it spread out and it flattened. So even though it's highly viscous, it still has some fluidity to it. It can still move. So that's what basaltic lava is like. It's very thick. In Hawaii, they actually refer to it, they call it ropey texture or pahoihoi. So it's just these big blobs, and they're thick, and they kind of twist and roll. And in the pictures are of Hawaii, so you can see what they look like when they erupt and when it's not erupting. Okay, so then there's cinder cones, or they're also called pyroclastic cones. These are formed of just pyroclasts, which are loose fragments, rocks, minerals, ash that gets exploded out of the volcano. So they're very violent, but it's like loose debris. So it builds up, but they're usually about a slope of 30 degrees. Because it's loose, it can't build a slope any higher than 33 degrees since there's gravity. If it gets any steeper than that, gravity just pulls it down. Although they're tall, few reach over 500 meters high. And what's interesting is these are very small, and they're common, and they can form on the flanks of other volcanoes. But again, they don't have a very long lifespan because it's mostly loose debris. So with weathering, they just kind of crumble and fall apart. So they don't last a whole long time. Composite volcanoes, which are also called stratovolcanoes, are a composite of the previous two. So you have layers that alternate, and you'll have explosions, eruptions that alternate. So it'll have a true lava flow, and then it'll have like a pyroclastic flow, or it's explosive. And these layers go on top of each other. Now, that loose debris, it doesn't fall off of these like it does on the cinder cone. And the reason why is because the next eruption is usually a lava flow, and it'll go over the top of it, and it holds it down, and it solidifies it, and it holds it all together. So as a result, these volcanoes get very, very large, and they can be very steep. They can rise to over 5,000 meters high, and they can be 6 to 12 miles across at the base. These take a very long time to build. And almost all the famous volcanic eruptions throughout history that you think of, Mount Etna, Mount Vesuvius, Mount St. Helens, these are all stratovolcanoes. And they're not necessarily even in composition. So just because it's a stratovolcano doesn't mean that it's going to be half lava flows, half pyroclastic flows. Each volcano is unique, and they will have different percentages of eruptions. So Mount Rainier is 90% lava flows and 10% pyroclastics. And Mount St. Helens is actually the exact opposite of that. So what makes the difference and determines those types of flows, a main culprit is the gas, which type of gas is being dissolved, and how much of it and how easily it can escape. Then we'll move on to a caldera, which is also called a crater lake. And this is an image from Crater Lake in Oregon. So when you have a fairly large volcano and it empties out the magma chamber fairly quickly in either a large explosion or a series of large explosions and eruptions, you now have this void in the volcano, and you have all this weight up on top of it. So you have a structural problem, and it can't support itself. So it eventually crashes in on itself. And then you get this hollow, and it'll fill with, over years, it'll fill with rainwater or even glacial water, depending on where it's at. And so you have this lake in the depression. Now, if the volcano has gone extinct, meaning there's no more magma, it's never going to erupt, it's near probably a subduction zone that doesn't exist anymore, then it's just going to remain a lake, and nothing's ever going to erupt again. But a lot of these form on volcanoes that are still active. So when that happens, the eruption occurs underneath it, and it's the water actually mixes with what's being erupted, and it makes it very fluid, and it allows it to move faster and more violently. Now, a lava dome, these are kind of cute. They're very bulbous, they're very round. They look like if you took like a basketball and cut it in half and set it on the ground. It's just this round thing. So it's not classic volcano shape. And what happens is in the eruption, the lava is very, very thick. It's so thick that it can't really flow. So it just kind of pushes out and sticks, and then some more comes out. And as it cools and becomes rock, more is pushing up underneath it, starts to crack and crumble and sort of roll down, and then it makes way for more. So it forms this very round shape. These can form in the crater of composite cones. So a lot of these smaller volcanic features can form within a larger volcano on the flanks or on the sides. In the magma chamber, we have a main vent that usually comes straight up. But depending on the volcano, they can have vents coming off on all the sides. And these can form smaller volcanoes on top of the large volcano. And about 6% of eruptions actually form these lava domes. And the picture of this one is from an eruption in Chile of a lava dome in 2008 to 2010. So types of eruptions. So there's two different types. There's the Hawaiian type, very slow, doesn't seem too dangerous if you stay away from it. And then there's the type like Mount St. Helens in 1980. Very violent, a lot of gas, a lot of ash. So those two different types are effusive and explosive. Effusive are our shield volcanoes. So it's just a gentle outpouring. The basaltic lava, it doesn't have much silica in it. It doesn't have a lot of gas in it, but what there is can come out easily. So it's very liquid. The gas can just come on out. It doesn't cause a lot of explosions. And it's very hot. It's about 1,200 degrees Celsius. So although it doesn't seem that dangerous, if you get in its way, it's obviously going to melt, burn, and cover anything in its path. And here's a little video. This is just going to show you in Hawaii an eruption, an effusive eruption. And this is the same type of lava that's creating more ocean crust. Although you wouldn't want to get close to it, it's actually an eruption that's kind of soothing when you watch it. It's not violent. And the opposite of that is the explosive eruption. So composite volcanoes, cinder cones, and lava domes erupt explosively. So it's a cooler magma it's much more viscous. It's much thicker, much more dense. Oh. And dissolved gases can't escape this type of magma very easily. So what happens is the pressure from that gas just builds and builds and builds until it finally has to come out. And when it does, you have an explosive eruption. When that happens, it blasts this rock and the minerals and lava into the air and a lot of ash. So you'll have anything from large cobble and boulder size down to like powdery ash, and it blasts it into the air. So before we take our break, let's watch this short little video, and we'll see an explosive volcanic eruption in Japan. Okay, now we'll take our little break since we're about halfway through.
A concurrent view
Okay, so now let's move on to volcanic gases. The gases that are belching out of these volcanoes. So roughly, each volcano is unique, but roughly it's mostly water vapor at about 78%, about 12% carbon dioxide, 7% sulfur dioxide, and then 3% other gases. Now, where the problems come in is with the sulfur dioxide that it spews into the atmosphere. When it mixes with rainwater, it becomes sulfuric acid. Sulfuric acid, it's highly reactive. It chemically weathers things very quickly. So it dissolves things. There's been examples of people living near volcanic regions where the hinges on their doors just get melted off. So depending on how much has been spewed out, it could become a real weathering problem. So this is a little snippet of the Papandayan volcano in Indonesia, which again is a stratovolcano. And you can see them go up and they're going to look at the gas. And you can see that it's very yellow. That's that sulfur dioxide.
Ooh, and this is steep here, isn't it?
Oh, yeah.
It's not just steep.
Super bloody maximum steep. Deep.
You see, Donnie learned most of his English from Eddie Murphy movies.
Wow! Donnie leads me to the gas vents. A fantastic display of the power that's just below our feet.
Now that sounds like a rocket engine.
Here at Papandayan, powerful volcanic steam blasts the sulfur to the surface, creating this exquisite display of color. Now I want to get right up in the gas field.
Let's go take a look. But that's so amazing. There's so much liquid sulfur in that one spot. It's just bubbling away. Inside these vents is a pond of liquid sulfur. And in its liquid form, it's orange. And when it comes up through the gas, it crystallizes and forms these yellow deposits that you see everywhere here. But the gas is so toxic. Woo! One of the edges, one of the fumaroles collapsed. I put my foot on it, and it showered me with sulfur crystals, and it blew right up into my face. Oh, wow. It's a good thing I was wearing these.
Yeah, he probably should have been wearing goggles going into an area like that. Okay, now it's not widely known, but volcanoes have their own index. It's the Volcanic Explosivity Index, and it's just like the Richter scale for earthquakes. So it's a scale of 0 to 8, and it takes into consideration many factors of a volcano. So the volume of the eruption, so how much magma and pyroclastics have actually come out. The height of the eruption column, so how high up is it shooting the magma and pyroclastics? So that would be how much power there is. And then how long the eruption lasts. So eruptions can last anywhere from a very short time measured in minutes and hours to all the way up to years and years. So it's a logarithmic scale, and that's the same as the Richter scale. So when you go from like 2 to 3, a 3 would be 10 times more intense than a 2. And the same for if you go from a 3 to a 4, it would be another 10-fold increase. So this is just an example of the index. You can find it online quite easily, and it just describes how much volume and what type of an eruption and how big the plume is and how long it erupted for. And then it gives you a few examples of some historical eruptions. Okay, so now we're going to go on to living with volcanoes, how volcanoes affect us. So energy and climate. The heat from the volcanoes can actually be harnessed as geothermal energy. So it's possibly an alternative energy source. What they do is they drill down so that they can trap and collect the steam, and then they pipe it to an area that has turbines. The steam turns these turbines and produces electricity. The United States is one of the leaders in geothermal energy. There's more locations where we're doing that than other nations, but it is something that's still being looked at as a major possibility. I mean, you have this heat, you can harness it, maybe it's worth a shot. But all forms of energy production, whether alternative or not, they all have their pros and their cons. And anytime you go drilling down into something and affecting nature, there's always repercussions of some kind. So it's still fairly new. And then, of course, there's dust and gas from the eruptions that can remain in the atmosphere for years. And they can actually affect the entire planet worldwide, depending on how great the eruption was, how long it lasted, and wind patterns. So, for example, in 1991 in the Philippines, Mount Pinatubo erupted, and the ash that it put into the atmosphere traveled the entire world. And it created these gorgeous sunsets everywhere for a while, which is great. It was pretty, but that ash also, it blocks solar energy. So it blocks the sun's rays from coming in. And it might be such a small amount that we don't even really notice it with our eyes, but it's enough that it can lower our temperature. So it's nice because it could cool the planet for a while and maybe stave off rising temperatures. But at the same time, you don't want something so cataclysmic that it cools the planet for a long time. And Mount Pinatubo actually lowered the world average temperature by 1 degree Celsius for several years. And in 1815, another volcano in Indonesia erupted, and it put so much ash into the atmosphere that the year 1816 around the entire world was known as the year without a summer. In New England, they actually had snow in June. So if you don't like hot weather, that might sound great, but the other side of that is we need those warmer temperatures. We need that solar radiation. We need that for producing food and agriculture. So it can really lead to famine and possibly even worldwide famine if it was on a great enough scale. So different hazards from volcanoes. So lava flows is probably what we most commonly think of, that hot lava, it burning and burying everything in its path. Of course, if you stay out of its way, you'll be okay. And then there's ash falls, so particles falling on you. Now, these can be large enough, they could hit somebody in the head and knock them out. They can break things. It could be fine sand like ash, but that can cause atmospheric and air quality issues. It can close airports. It can cause damage. Pyroclastic flows. There's explosions. You can get buried from the debris. Lahars, that's when the volcano mixes with rainfall, or it can quickly melt glacial waters. These waters mix with the lava, making things much more fluid. They can move faster. It lubricates the lava, making things more dangerous. And although we usually think of tsunamis being caused by an earthquake deep in the ocean, they can actually be associated with volcanoes as well. If you have a volcanic eruption in the ocean basin deep in the sea, and it's great enough that it displaces a lot of water, that water can rise up and move towards land as a tsunami. So tsunamis caused by volcanoes are much more rare than caused by earthquakes, but it is a risk with volcanoes. And then, as we said before, weather and climate, you can have cooler temperatures, shorter growing seasons, and possibly even famine. And then air quality, pollution, the sulfur dioxide that can chemically weather things. So there's a lot of hazards, but it also creates new crust, new land, fresh beginnings. It can add mineral content and nutrients to the soil. It can make the soil richer. I mean, think of how beautiful Hawaii is with all those rich, lush plants. They're feeding off all of that mineral content from the solidified lava. So there's good and there's bad with volcanoes. So now we'll get on to the funnest part of the lecture, in my opinion, the historic volcanic catastrophes. So I'm going to go over, well, I've got a short video first that's going to cover the 5 worst volcanoes in history. And then after that, I'm going to cover a few more. So we're going to look at what caused them, when they occurred, where they occurred, what type of volcano. Okay, so these are the 5 most deadly eruptions that ever occurred. 1902, Mount Pelee in the Caribbean. It was very quick. It was an explosive eruption, and it killed everyone on the entire island. It just covered everything. And then 1883 in Krakatoa, Indonesia. 1815 in Mount Tambora, Indonesia. 1600, and I'm not even going to try to pronounce that one, in Peru. And 1783 in Laki, Iceland was the absolute worst. So here's a little video that's going to show you a little bit more about each one. Okay, so here's one that we've all heard of before, Mount Vesuvius. And it erupted in the year 79. So it's in Italy. It was a 5 on the Volcanic Explosivity Index. That's pretty high. So it was a major explosion. It was a stratovolcano, so it would have been an explosive eruption. It killed 3,000 people, estimated, and it basically covered the cities of Pompeii and Herculaneum completely in 5 to 8 meters of hot ash. And we've all seen those touring like museum shows from Pompeii where they have the people that were preserved, basically solidified in the hot ash that covered them. So it was also, it's still active, and some people say that it was erupting from 1631 all the way through 1944, and it remained somewhat active. But the actual eruptions were big eruptions were 1906, 1929, and 1944. Now, the scary part in this, and the part I don't understand, is it's one of the most dangerous volcanoes in the world, and the city of Naples sits right at the base of Mount Vesuvius, and it's still active. So it's very scary to think what could happen. I wouldn't want to live there. I don't want to live near a volcano. But yeah, so it's also the only active volcano on mainland Europe. There's also Mount Etna, but that's in Sicily. So this is a short little video about Mount Vesuvius and the eruption in 79.
Mount Vesuvius erupts in AD 79, destroys the city of Pompeii, all the farmland around it, and all the people in it. And we have in the exhibition a real person from Pompeii who died in AD 79. We call her the Resin Lady, and it's very sobering when you think that this poor woman actually lived the day of the eruption. And she would have been terrified. She ran with 60 or so other people into a big storeroom, and there they died. The eruption of Mount Vesuvius was deadly, and it created a great volcanic cloud. As long as that cloud was up in the air, they were okay. But when the cloud collapsed, it created what's known as a pyroclastic surge. And this is a superheated 300, 400 degrees centigrade avalanche of ash and rock and gas traveling at 70 miles an hour and 300-400 degrees heat. And nothing could survive it. And the Resin Lady and all the people with her died instantaneously. Pompeii is so important because, first of all, it preserved so much. Before the great volcanic cloud collapsed, the cloud dropped a lot of the stones it was carrying, small volcanic stones, the remains of the volcano that had been pulverized and thrown up into the air. And it drops it like rain. And this builds up about 30 centimeters every hour. And what this does is to preserve things. So even very fragile things like glass jugs or fine pottery get covered by the ash, building up gradually. The wall paintings, the mosaics, all get buried by the ash, and that preserves them. So that when the great volcanic avalanche comes down and sweeps things away, destroys things, everything that was below the stone was preserved. So Pompeii is important because it gives us this snapshot of what life was like. Pompeii wasn't a special city at all. It was special because it was buried by the volcano. That's why it's important for us. The other reason Pompeii is so important is because it's an ordinary city. The Romans are us 2,000 years ago. And that's why Pompeii is so important, because it brings the Romans close enough that we can almost touch them.
Okay, now Mount Kilauea in Hawaii erupted in 1959, and it was an effusive eruption, so that very slow moving, heavy, thick basaltic lava. So it was only a 2 on the volcanic explosivity index, and it was very short lived. It didn't last too long, but the amazing thing is it formed a lake of lava, and we're like 61 years later, it is still cooling. It was that hot. So now we're going to see that one explode here. So the gases are causing the lava to come up into the air like that. But since this lava is, even though it's thick, it's not as hard as the pyroclastic flows, the gas can easily come out of it, so you don't have those massive explosions like the others. As that lava cools and solidifies and lithifies, it's creating more of Hawaii. So it's getting bigger. And it's all coming up from one hot spot. And the eruption of Mount St. Helens in 1980. It was very explosive, and of course that was in Washington in the US. It was a 4 to a 5 on the volcanic explosivity index, so definitely one of the most explosive, at least in modern times. And again, it's another stratovolcano, so very violent when it explodes. And it produced a monumental blast that was so great that within 10 seconds, it stripped an area that was 10 kilometers of all the soil and all the vegetation. It just blew it out. And unfortunately, there were 63 people killed. including a graduate student who was studying volcanism, and he was taking measurements of the volcano. So even though they evacuated, because they knew it was going to explode, so they evacuated, but there were still a few people there that got killed. So it decimated 600 square kilometers. It's still active right now, but there's no signs and no indications that it's going to erupt anytime soon. So most of these active volcanoes, they're monitored and watched, but predictions have gotten much better in recent times than they used to be. But they can't say for 100%, 100% sure it's going to explode on this day. Just don't know. So it's still active. But before 1980, the last time it erupted was 1857. So it's not a frequent erupter, but you never know. And it was formed and it's kept active by the subduction of the Juan de Fuca plate going underneath the North American plate at Washington. So the plate is being subducted under, and as it gets deeper, it gets hotter. So it's starting to melt the Juan de Fuca plate, and it melts it into magma, and then it's coming up into Mount St. Helens. And here's some footage of the actual 1980 eruption of Mount St. Helens.
Almost 10,000 feet tall, Mount St. Helens is one of several active volcanoes in Washington's Cascades mountain range. By 1980, it hasn't erupted for over a century. But beneath its serene exterior, Mount St. Helens is beginning to stir. On March 27th, red-hot magma from deep within the volcano rises high enough to come into contact with icy meltwater.
No matter where you are on Earth, there's beneath you somewhere, there's water. So if something hot comes up into that water, it heats it up. It can build up enough pressure that it finally just breaks through as an explosion, like a pressure cooker, you're just letting loose.
Most scientists expect that if the mountain does blow, it will be in a classic vertical eruption, affecting only a limited area close to the volcano. But the mountain could explode sideways in a lethal lateral eruption, devastating a much larger area. At 8:32 a.m. on May 18th, 1980, they get their answer.
We are directly above Mount St. Helens now, and there is no question that the volcanic activity has started. Smoke.
A massive earthquake causes the huge bulge on the mountain to collapse, removing a mile-wide chunk of the north face. With an energy equivalent to 1,500 Hiroshima atom bombs, rock and superheated gas shoot from the volcano at terrifying speeds of up to 400 miles per hour. Such is the force of Mount St. Helens' lateral eruption that an incredible 1,300 feet of mountain disappears almost instantly. Now the eruption enters its next phase. Expanding magma inside the volcano sends thousands of tons of scorching rock and gas high into the atmosphere. A dense plume of ash stretches 15 miles high. The choking ash fills the air outside, turning the sky dark. Breathing becomes almost impossible. In the minutes after the eruption, 46 billion gallons of icy meltwater start to pour down the mountainside, gathering rock and debris to create a lethal slurry called a lahar. The deadly lahar becomes a massive tsunami of destruction. Scientists scramble into the air to get an overview of the unfolding disaster.
I was awed by what I was seeing. We could see this tremendous eruption column and all the energy that there must be in it.
Navigation is almost impossible. The ground below now bears no resemblance to any of their maps.
There were lots of fires burning. Within the cloud, there were mixtures of ash and rocks, boulder rocks from the volcano. and a lot of steam from melting glacial ice.
Mount St. Helens continues to erupt until late in the afternoon. Ashfall forced towns and cities up to 300 miles away into a state of emergency shutdown. In just over 2 weeks, the ash circled the entire globe. Officially the deadliest, most destructive volcanic eruption in U.S. history, the eruption ultimately claimed 57 lives.
And Mount Pinatubo in the Philippines erupted in 1991. It was the second largest eruption of the 20th century. And it was a 5 to 6 on the VEI. So it was a very, very violent, very powerful eruption. And again, we have another stratovolcano. They evacuated, so they estimate that they saved about 5,000 lives. This particular volcano put forth large amounts of sulfur dioxide, polluting the atmosphere. And the airlines in the area, the ash caused them $100 million in damage from the planes sucking in the ash. And the last time it erupted was over 400 years ago. So it doesn't erupt that often, but it's a very violent one when it does. And so this is a little news piece, a British news piece, showing the devastation in the area afterwards.
A desolate and eerie landscape in the northwestern Philippines. It looks like the aftermath of a nuclear holocaust. Instead, it's the wrath of Mount Pinatubo, a volcano that rained down over towns and farmlands, killing more than 300 people, leaving thousands more homeless, and casting a shadow over the future role of the US on the island nation. The angry giant awoke on June the 9th after a 611-year slumber. A mushroom cloud of steam, ash, and smoke rose 30 kilometers into the sky. Dozens of eruptions rocked the region. As it settled, the debris blotted out the sun and coated hundreds of kilometers of Philippine countryside with what looked like snow. Many locals stayed in their homes around the base and slopes of the volcano, in spite of warnings to leave. Others fled for their lives as Pinatubo reawakened. Frightened and helpless, villagers fled to nearby towns and into the capital, Manila, leaving their homes to the mercy of the mountain. They left however they could, taking what little they could carry.
This is the city of Olongapo at 9 o'clock in the morning. It's 25 miles from the volcano. The power's been cut, people queue for fuel, for lamps and generators. In the shadow of the mountain, it's raining mud. Wet ash covers everything. The rivers are brown, flowing under relics of a previous natural disaster, the earthquake a year ago. Under threat from the mud flow and ash cloud, hillside villages are evacuated. A number of tribesmen are reported buried under the mudslides. Others arrive at evacuation centers to be reunited with lost relatives. Nature is conspiring once more against the people of this country.
And now Mount Etna, which sits on Sicily. It erupted continuously from 1991 until 1993. And then it started erupting again in 2013, and it's still erupting today. So it's only a 1 to 2 on the volcanic explosivity index. So it's not all that violent, but what makes it so noteworthy is how long it erupts. And And again, it's a stratovolcano. It's violent, but it's not as violent as the other ones that we've seen. It's calmer. But it's one of the world's most active volcanoes. And it actually erupted for 473 days straight one time. And that was between 91 and 93. And when it did so, it extruded over 300 million cubic meters of lava. So that is a lot. And it's formed between two plates. The African plate is subducting underneath the Eurasian plate near Sicily. And so the African plate is melting where it subducts, and it's coming up as Mount Etna. So this is a short ABC News video showing the actual eruption in 91 to 93. And you can see, even though it's exploding, it's not as powerful as Mount Pinatubo or Mount St. Helens that we just saw. And it's not flowing like the shield volcanoes of Hawaii that we saw. See, it's much thicker, the lava that's coming out. It's very thick. It solidifies quicker. And this particular slide, it got a little excited and thought that it was going to be in next week, and it says earthquakes in 2020. So just pretend that says volcanoes. So a lot of people are shocked to find out that in 2020, there were 55 volcanic eruptions already. I mean, we don't necessarily see it every day on the news or think about it, but there's volcanoes erupting every day. And in 2020 so far, there's been 11 new eruptions. So those were coming out of volcanoes that have never erupted before, or new volcanoes, or sometimes even volcanoes that are thought to be extinct can renew in their volcanism. So right now in the United States, we have 3 volcanoes erupting right now today. And they're all 3 in Alaska. So these aren't huge eruptions. They're not all that exciting, but they are erupting right now. And so I want to show you a website that you can go on, and it's from the Smithsonian, their Institution on Global Volcanism. And you can look up any volcano in the world. You can look up what's erupting today in the US. You can look up what was erupting the year you were born. You can look up all kinds of different facts about these volcanoes. And what makes this website so fantastic and fun is that you can click on the name of the volcano and it'll take you to Google Earth and it shows you the volcano right now. So you can have a look at it. And it also gives you all kinds of facts about it. So hopefully this link will work right now. Good. Let's hope. Is it going to open? Okay. So at the top, it says this is Mount St. Helens 40th anniversary. So I was on the page of what was erupting this year. And this is a list of all the volcanoes that are erupting. And if it says continuing, that means that it's still erupting. And so you can just click on the name. And then when you go down here, there's a list of questions. And if you click on them, it'll take you to the information or the volcanoes that answer the question. So like longest eruptions, how many active volcanoes are there right now? Is volcanic activity increasing? Things of that sort. And what was erupting in the year. So you can enter any year and see what was erupting. So let's have a look at the Cleveland volcano. This is one that's erupting right now in Alaska. So as you can see, it's not real exciting right now, but that is it, and it is erupting. And it'll tell you the volcanic region, the type of volcano, the last known eruption date, where it's located, how tall it is. You can go down here and you can click on more information about the volcanoes. So for looking up volcanoes, this is the best website there is. So you can have some fun with that one. Okay, now we're going to go on to eruption forecasting and some local concerns for us about volcanoes. So eruption forecasting, it didn't used to be all that great. Right now, there's a handful of observatories around the world. Oh, what is that? Just close it. So there's a handful of observatories around the world. They monitor the volcanic behavior, and they do so by measuring the slope of the mountain. When the magma starts to build and get hotter, it kind of bulges out a little. So the slope changes. So they take a lot of measurements of the slope. Earthquake activity, when things start to rumble and move down there and start to shake a little bit, that can be a tip off that, it's getting a little upset. Some gases are moving around, it's getting closer to erupting. They measure the gas content that's coming out of the volcano. And they can also measure the swelling with satellite imagery. And so far to this day, the satellite imagery has been the best tool for predicting these. And they can do pretty well with them. And in most cases, they can evacuate before a catastrophe occurs. But forecasting of anything, whether it be weather, earthquakes, volcanoes, it's not perfect. And they're just educated guesses based on the tools and the data that they have. But they're definitely getting better and more accurate. So we're in Kansas, so it doesn't seem like we'd be at any risk or have volcanoes affect our life in any way. But they actually could in some of the ways we've seen before: atmosphere, agriculture, in those ways. But what's interesting is in 1999, some researchers from the Kansas Geological Survey were taking measurements and doing research in Riley and Marshall counties, and they discovered 3 ancient volcanic features. So they're not active by any means. They were extinct many, many millions of years ago. But they discovered 3 kimberlite pipes. Kimberlite pipes are named for an area in Africa called Kimberley, which is where a lot of diamonds are found. Kimberlite pipes are basically a pipe where magma is coming up. So they're a little different than a traditional volcano, but they are a volcanic feature. And they're usually bringing magma from an extremely deep location, deeper than your average volcano. And that's why they're why they bring up a lot of diamonds, because, diamonds need that pressure. They're found very deep. And so they found 3 of these pipes. Unfortunately, no diamonds. So all the diamonds from the kimberlite pipes are still in Africa. We didn't get any. But so we did have some volcanic activity at some point. We don't have any right now, but we are close to Colorado, and Colorado has several active volcanoes right now. And they have one, the Dot Cerro Volcanic Center. It's active, but the last time it erupted was 4,100 years ago. It's not believed that it could erupt anytime soon, but things do change, things happen. That's our closest volcanic risk. It's about a 3-hour drive from Denver, so I've never been there, but I hope to at some point. So that wraps up the lecture on volcanoes, and next week we're going to talk about earthquakes. So now we're ready for questions. Oh, yes. Yeah, actually, Yellowstone was it was a very, very big catastrophic volcanic explosion at the time when it was created. It has a lot of activity going on. I mean, the geysers, the heat from it, and a lot of scientists do believe that at some point it could explode. It's been getting a little more active lately, so it is a risk. I mean, we're not that far in terms of volcanic explosions. We're not that far away, so that would definitely be a catastrophe if that happened. Yes. Oh, sure. Let me go back to it. Yeah, it's volcano.si.edu. Yes. What? I'm sorry, I didn't hear the question. Oh, she asked, where are the volcanoes in Alaska? Well, they are in different locations, but they're all in one mountain belt, and it's another subduction zone. So it's inland from the subduction zone. And if you go to that website, it'll tell you like exact latitude and longitude where each of them are. Did we have any online questions, Pat? Okay. Are there any other questions? Okay, well, in that case, I'd like to thank you all very much. And next week, we're going to do earthquakes. And I think you have an announcement for them for location?
I just want to remind everybody that next week we will be meeting in room 180. And so that's on the other side of the building, and you will enter at doors D or N. So you'll look for the D or the N, and that's where you will enter the building. This week we had to move you because this is a polling site tomorrow. And so room 180 is full of voting machines right now and people getting ready for the election tomorrow. So we appreciate you bearing with us today and being a part of our very first class where we've done hybrid, where we've been streaming and having people here in person. And we look forward to seeing you next week. So thank you.